many years. He's a theoretical physicist, and his CV is too long to memorize, so I'm cheating as always. He did his bachelor's degree at UCSD, San Diego, and then in 1999 he got his PhD from MSU, from Michigan State University, working with CP.UU, not from CP violator, like he used to say. Then from 1999 to 2002, he was a research associate in the High Energy Physics Division at Argonne National Laboratory. From 2002 to 2004, he was a research associate at the theoretical physics group in Fermilab. At that point in time, we started coinciding with him a lot because many people from the group were there. Then from 2004 to 2009, he was an assistant physicist at the HEP division, again at Argonne. From 2006 to 2009, he was, together with the Argonne position, assistant professor at the Physics and Astronomy Department in Northwestern University in Illinois. And then from 2009 to 2011, he became assistant professor in the Department of Physics and Astronomy at the University of California at Irvine, where he is actually now. In 2011, he became an associate professor. In 2013, he became a full professor. And since 2017, he's actually the vice chair of the graduate student, maybe the chair already, right, of the graduate studies, or vice chair?
Yeah, vice chair of the
graduate student studies of the physics department at the University of Irvine. He has worked a lot on, well, particle physics and cosmology. He's an expert in dark matter, WIMPs, and SUSI, everything, Higgs. So he gives a talk. Very nice talk. It's a good time to check that the telephones are muted. Like in the cinema.
Thank you very much. It's really very nice to come here to visit Santander and so many of my friends from the old days. As Gervasio mentioned, we were at Fermilab together, and it was a bunch of experimental physicists, and I was the theoretical physicist, which meant I got all of the questions. So as a result, I got used to explaining things. So today I was asked to say something about connections between particle physics and cosmology, and I broke that down into mostly dark matter, but also a few other things that I think are interesting and some overview. So hopefully that will be interesting. The most important question always on the first slide is that the animal you see up there is an anteater, the one that eats ants. And that is our mascot at UC Irvine. I don't know why you would choose an anteater as a mascot, but it's okay. At least it's a mean-looking anteater. Okay, so here's an outline of what I want to talk about today. Introduction is really just to emphasize the fact that if we talk about very, very early cosmology, this is particle physics, and so we need to use the language of one to talk about the other. That's where all of my expertise is. And then I'll talk about a few different topics that are related to that fact. So I'll use Big Bang nucleosynthesis to explain something about what we know about baryogenesis, and that will make me talk about the electroweak phase transition. And then finally, I'll talk about dark matter. So these are somewhat disconnected topics in some ways, but hopefully it's interesting. If you have questions, I'm happy to take them as the talk goes along or also afterwards, whatever you think is better for you. And I guess there's a question section afterwards with the students, so that's good. So of course, you've probably seen a diagram like this one. I just searched on Google, and there were about 10 different versions of this, so I picked the one that I liked the best. But I only spent about 5 minutes looking at them, and they were really little on my screen, so maybe I didn't choose the right one. Basically, it shows what we think we understand about the history of the universe, starting from the Big Bang, when everything was very, very small and compressed, all the way to today, the universe that we see around us. And there are different things going on here that I'll talk about very briefly. But the real thing that we have to remember when we think about cosmology in the context of particle physics is really just that we know the universe has been expanding for its entire history. At least we think it's been expanding for its entire history. And so as we go to earlier times, we go to a smaller universe with higher temperatures and therefore higher energies. So there are some observational things that we're pretty sure must have happened based on what we see in the universe. We know that at late times, and again, this is late by my context, if you actually are someone who does cosmology for a living, then this might actually be early from your point of view. Everything is relative. But atoms formed at a certain point. This is when the cosmic microwave background essentially took the form that we see today. And that's great because it teaches us actually about what the universe was doing very precisely at that moment in its history. But it's also annoying if you want to know about earlier things, because it means that before that time, you really can't use anything that's charged or photons to learn about the universe. So the cosmic microwave background is a perfect fossil record, but it's also a screen that it's hard to go earlier than. However, we do have a few hints about things that may have happened earlier. So for example, we're pretty sure that at some point, the protons and neutrons that were in the universe formed some primordial abundances of light elements. So this is mostly different isotopes of helium, but also some elements like lithium. And so when you look at all of the universe, right, obviously there are places where the elements are concentrated like stars, but also in general, spread throughout the universe, you see there's a primordial abundance of these elements. And this really agrees with what we learned from nuclear physics and tells us that the picture of the universe having been expanding at the rate we expect is really true at the time of these nuclei being formed. And it's really the earliest thing where we have a very concrete evidence of what was going on in the universe at that time. That was happening at a temperature of a few MeV. So everything earlier than a few MeV, right, or higher temperatures, becomes much more uncertain for us. And then we also have evidence that inflation took place, and it left some consequences actually in the cosmic microwave background. But we think there's a period where the universe expanded very fast. I'm not going to say anything about that today, but that's also a very interesting topic in early cosmology. And there's a lot of model building to try to understand what can we learn about the different ideas for how that could have happened. Of course, right now we measure that our universe has some dark energy. I'm not going to say anything more about that either, but that means our universe is also now inflating. It's just inflating a lot more slowly than it was back then at that early time. Maybe those are connected and maybe they're not. I think we just don't know. So there's also a bunch of things we think are likely to have happened, but they happen at earlier times than nucleosynthesis, and so we don't have very much observational evidence for them. So for example, we know that if we take a bunch of protons and neutrons and we make the universe very, very small and we make them very hot, eventually they have enough energy that they break apart into quarks and gluons. So at some point in the universe's history, the quarks and gluons turned into nuclei, and this is what's shown here. These little blue and red circles are protons and neutrons with little quarks inside. So you see earlier than that, these things are just broken apart into quarks and gluons. We're pretty sure that probably happened. We're not actually positive. That maybe the universe was never hot enough for this to happen, but I think many people would be surprised if that were the case. We think that we know there is dark matter in the universe. We think at some point it probably froze out, so its abundance got fixed by some fundamental interactions. We know that our universe has an asymmetry between matter and antimatter in it. We don't know where that came from, but we think it probably was generated from some physical process, which is called baryogenesis. And we also think that if we go to very, very early times at high temperatures, the electroweak symmetry, so that's the symmetry for the electroweak interaction, becomes exact. And when that happens, the W and Z bosons are massless. The quarks and leptons are all massless. So we think in the early universe, all those masses were exactly zero. And then at some later time, there was a transition, and we turned into the universe we have today, where all those particles got masses. So I'm going to talk not so much about this. I'm going to talk a little bit about these three with an emphasis on the dark matter. Okay, so here is a less graphical but maybe more informative way of looking at that. This is the universe in temperature from about 100 GeV down to today below an electron volt. So there are many, many orders of magnitude here that are changing. We have the CMB, which is really a reflection of the atomic physics at the time. Big Bang nucleosynthesis is telling us about nuclear physics, right? That's a time when nuclear physics governed the universe. And everything earlier than that is usually the domain of particle physics. So for example, when QCD goes from going from quarks and gluons into protons and neutrons, confinement, that's the beginning sort of what we call high energy physics. Dark matter freeze out, we're not exactly sure when that happened, but it's probably described by high energy physics. And then things like the generation of the baryon asymmetry and the electric phase transition, those are definitely high temperature things that must be described by particle physics. So my history is that I started out as a very traditional particle physicist. I did things like Large Hadron Collider calculations and supersymmetry. And then as time went on, I got very interested in this question, largely because I realized I could understand what the people working on this stuff were saying when they were talking to me, and so I realized their problems are very exciting, and that's why I started to get interested in this area of physics. All right, and so this just says the same thing I said before. Before Big Bang nucleosynthesis, which is usually abbreviated as BBN, Most of what we know about it is extrapolation based on what we know was happening at that time. And then if you know what your theory is, so in this case the theory is the standard model of particle physics, then you can imagine that if I start with this condition and then run the movie of the universe backwards to higher temperatures, you can predict what's going to happen. So in principle, if the standard model is the entire story, we know what the universe should look like as a function of the temperature, up to some inputs like what temperature did it start at. We're not really sure about that, for example. Okay, and part of the reason why we're excited about things like inflation, dark matter, primordial gravitational waves is something that we hear about a lot lately, and the existence of the baryon asymmetry is they are all hints as to what was happening at the earlier times. So there's something about particle physics you can learn by looking there. So let me say a little bit about baryogenesis and nucleosynthesis to begin with. If you look at experiments, they show that this parameter called eta, which is the number of baryons minus the number of antibaryons normalized by the entropy, is a small number. It's about 10 to the minus 10. So there's almost exactly the same number of baryons and antibaryons compared to all the stuff in the universe. But it's not zero, and it's very significantly different from not zero. So we know that actually our universe is made out of baryons and not out of antibaryons. And I'll say a little bit about the observational evidence for that in the next slide. But there are some indirect things that argue for this number as well. If you just look at the cosmic rays, and of course this is not entirely well defined because I should tell you what energy these particles have. The ratio is a function of energy. But if I ask about the antiprotons versus protons, there are about maybe one antiproton for every 10,000 protons. And this is consistent with the idea that our universe is made out of protons, but because some of the protons get accelerated to high energies by things in the universe, you know, like pulsars or active galactic nuclei or stuff like that, they get accelerated to high energies, and that produces some antiprotons just in the interactions. And that would roughly explain this number. Also, just the fact that our universe exists at all, if we had equal amounts of baryons and antibaryons, then they would start finding each other and annihilating. They would produce things like pions and photons and so forth. And basically, they would have all gone away. They would have been entirely gone, such that we would have about 10 to the minus 20 as the density. And instead, we have something that's more like 10 to the minus 10. So the fact that our universe is here and is not empty is also a consequence of the fact that there was a difference between the baryons and the antibaryons. So this is the usual plot you see where people are looking at Big Bang nucleosynthesis. And the reason these two things are connected is because, so Big Bang nucleosynthesis, like I said before, is the process of creating the light primordial elements. This one labeled Y is really the fraction of helium-4. Then we also have deuterium, helium-3, and lithium-7. Those are all long-lived enough that they're still in the universe today when they were produced at early times. So these curves show you how much of these elements you would predict there to be as a function of this ratio of baryons to photons. So this is that measure of the asymmetry that was about 10 to the minus 10 or so. So the curves are theoretical predictions based on using nuclear physics. You measure the cross-sections, and then you can predict how much of these things you should have. The CMB is a different measurement that I'll talk about on the next slide. But the point is, and then the yellow boxes show experimental determinations where you go out and you just look how much helium-4 is there in the universe, how much deuterium is there. So there's a very big error bar here on this measurement. It's hard to see, but this blue line has this really, really tiny yellow box. It's about the same precision as the CMB is. That makes it kind of even harder to see. And it's really what drives the fact that we prefer this value of the asymmetry on this plot. But what you can see is that other than maybe lithium-7, which is only off by maybe a factor of 2, and these are hard measurements to make because anything else that produces lithium-7 will pollute your measurement, everything seems to pretty much agree between the measurements of the different elements and this value of the asymmetry that we have at about 10 to the minus 10. This fact down here that lithium-7 seems to be a little bit off is sometimes called the lithium problem. And there are people who build models of physics beyond the standard model to try to move the prediction for lithium over so that it would agree with this value. I'm not someone who really spends a lot of time doing that, but these models are interesting because they all involve physics around the MeV scale, because this whole process is nuclear physics, and so it happens at a temperature of about an MeV. So you know that if you want to affect it in a big way, you really need to change the physics at MeV scale, and that's exciting because, of course, MeV is not a very high energy from the point of view of the laboratory. So you can actually learn about these theories by doing experiments. This plot is actually kind of a cartoon. It shows you the Doppler peaks of the cosmic microwave background as a function of the multipole. Right? This is a multipole expansion of the CMB correlation function. This is very old data from WMAP. Nowadays, the Planck data is very precise. The problem is it's so precise that your eyes would not be able to see what I'm trying to show you on this plot, and that's why I have the old one. It shows you that if you change the number of baryons by plus or minus 15%, your prediction for the height, especially of the first peak, varies by quite a bit, and it's enough that even at the time of WMAP, you could see that you could not actually raise that value by 15% or lower it by 15%. That would be inconsistent with the data. And now with Planck, more precise measurements, it's even more constrained at that point. So the point is that value we saw on the previous slide from CMB is also a very precise measurement from cosmology. So yeah, I like this plot because it illustrates that point. So this origin of the baryon asymmetry is a very interesting question for particle physics. We know it has to exist at the time of MeV scales because that's when the nuclei were forming. It could be that the baryon asymmetry was an initial condition of the universe. We don't really know where the universe came from, so it may be that it was just born with an asymmetry in baryons and antibaryons. Of course, as a physicist, I think we would all find that very mysterious, but we can't rule it out as a possibility. However, this idea is hard to reconcile with the idea for inflation. So remember, inflation was a period where the universe expanded in size very rapidly, in fact, exponentially fast. When the universe expands so fast, all the stuff in the universe basically goes to zero because you talk about a density. If you make the volume grow infinitely fast, or close to infinitely fast, it doesn't matter how much density you had to begin with, you're going to end up with nothing at the end of the day. And so any asymmetry we had was probably erased by inflation for that reason. So we know that inflation probably happened, and therefore it's very difficult to reconcile that with the idea that there was a primordial asymmetry. So that means that we have to somehow, after the physics of inflation, have something that will generate the asymmetry for us. And that means that it's a problem for physics to solve. It's not, you could argue that maybe the initial condition is like invoking religion, right? This is just how it was made. But because of inflation, we know that something happened between us and whenever the religion was active such that we lost our religion, unfortunately, our religious explanation. So we need to have some physics to generate the asymmetry. And we also know that it has to happen at least by energy scales of about an MeV. So it could be higher, right? It could be an earlier asymmetry that was generated, but it has to at least have taken place by that temperature so that we have it ready to make the protons and neutrons and then the helium and so forth that we saw before. So the three conditions that are required if you're going to start from a universe that is symmetric in baryons and then generate a universe that's antisymmetric in baryons were actually elucidated by Sakharov in the 1960s. I don't know if you've ever studied the history of Sakharov. He was a very interesting person. He was actually very politically active as well as a physicist. And his political philosophies would seem very enlightened by the standards of today. I understand you guys have an election coming up. I hope it goes better for you than it went for me. Anyway, so the three conditions are, if your theory starts out, if your universe starts out with equal numbers of baryons and antibaryons, but you want an asymmetry, the first thing you have to do is you have to violate baryon number. And that's kind of obvious, right? If I can't create a different number of baryons and antibaryons, obviously I'm never going to get anything that's different from symmetric. So that one's obvious. Then there are two others that are not quite as obvious. Your universe has to have charge and CP violation. And the reason is if you don't violate both of those symmetries, then the sum of all the processes that create baryons are guaranteed to be balanced by the processes that destroy baryons. And so even though in principle I can change the number of baryons, I'm not going to unless the universe violates CP such that there's a difference. Right? You might have heard in quantum field theory class that CP times time is a conserved quantity. That's true if Lorentz symmetry is exact. So if you violate CP, that's the same thing as violating T. And that means the universe is not the same if you run it forwards or you run it backwards. And that makes more sense than you can understand that that would be a good condition if you want to favor creation of baryons or antibaryons, right? The first one tells you that it can change with time. The second one tells you that it makes a difference if you're going forward in time or backward in time, and so it favors one or the other. And then the last one is that your universe has to have some processes that are out of equilibrium. And that's, again, because if they're in equilibrium, then they're just going to settle down to some point where the number of baryons and antibaryons are going to be violated by the same number. So we need the universe to be out of equilibrium in order to generate a net baryon asymmetry. So that brings me to talk a little bit about the electroweak phase transition. It turns out, actually, that the standard model has all the ingredients inside it that could actually explain the baryon asymmetry. And people were very excited when they found that out, because they thought maybe we already have everything we need to explain it. It turns out that we don't. It turns out that the standard model doesn't actually work, but it's very interesting to see how it tries and what the failure can teach us. So the standard model, of course, violates charge conjugation and CP maximally. Well, these are the hallmarks of the electroweak force, right? So charge conjugation is violated because the W boson's coupled to the left-handed quarks, but not the right-handed quarks. CP is a little more subtle, but we know that we have experiments looking at, say, B meson oscillations precisely to measure CP violation, which again are coming from the electroweak force, but they only occur at loop level, so they're a little more subtle. Then there are non-perturbative electroweak processes that actually change the number of baryons, and I'll say something about that in 1 minute. And then at a temperature of about 100 GeV, as I mentioned before, the universe goes from an electroweak symmetric to an electroweak non-symmetric state. So what happens is, at early times, the Higgs expectation value is 0, and everybody's massless. And at late times, the Higgs expectation value turns on, and everything gets massive. And the process where you go from one to the other can actually be out of equilibrium. And so this allows you to satisfy the last Sakharov condition. So first, let's talk about the baryon number violation. There are objects in the quantum field theory called electroweak instantons that violate baryon and lepton number. These are very hard to visualize in your head, because when you study quantum field theory, you learn about Feynman diagrams, and these don't actually happen inside Feynman diagrams. If you just talk about particles, you can't actually see that these processes happen. However, if you remember that quantum field theory is actually a theory of fields, there are very weird knots. They're like a set of W and Z field that's turned on in some region of space, and they're kind of knotted up in a strange way. These were discovered by Tufte, who won the Nobel Prize for his work on the electroweak theories of normalization. But there are these weird knots of these fields, which are sometimes called either instantons or they're called sphalerons. And it doesn't really matter the distinction between those two words. They're very similar things. And what these weird knots, so this little circle here in the middle represents one of these knots of W and Z. They create or destroy 3 quarks of every family and 1 lepton of every family. So if you wanted to take into account this kind of process in a Feynman diagram, you draw a Feynman diagram like this one, where you have your 3 families. 1 quark of every color from every family is attached, right? And of course, it could be an up quark or a down quark. If it's the first generation, it could be charm or strange or top or bottom. And then 1 of the leptons of every family, which again can be chosen to be either the charged lepton or the neutrino. So because they're mediated by a field configuration of the W and Z boson, they're very suppressed by the large W and Z masses. So theoretically, we can see that these processes take place in the standard model, but experimentally, we've never actually been able to measure them. And they're just too suppressed. They happen too slowly. But in principle, they do all sorts of crazy things, like they let nucleons decay, because you can turn these quarks into, say, like a proton, a neutron, and another proton or something. Then that set of 3 guys can decay into some number of leptons. And that's predicted to happen. It's just never been observed. OK. So the standard model really does actually violate baryon number. What this does, right, is that each 3 quarks together has baryon number 1. So it takes 3 units of baryon number, and it turns it into 3 units of lepton number. The standard model also has the electroweak phase transition, and the details of the phase transition depend on the Higgs potential at different temperatures. So if you calculate, so this is the Higgs field value, and this is the potential energy. If you calculate what the potential energy looks like for different temperatures, at low temperatures we know that the Higgs potential favors there to be an expectation value for the Higgs right? And this non-zero value here is what gives mass to everybody, the W, Z, and the quarks. If I go to higher temperatures, though, what happens is you have to imagine that now I'm looking at the potential for the Higgs, but at high temperatures, there's a gas of particles there. And if I turn on the Higgs vacuum expectation value, the particles in that gas get heavier, and that costs energy. So at some point, if you have enough particles stuck into your box with a high enough temperature, the Higgs says, well, I would rather just turn off my expectation value altogether because that will cost less energy, given all these particles here that are getting mass when I do it, than just having the expectation value that my potential wants me to have. And so the way that that looks is if you look at the effective potential for the Higgs, as you go to a little bit higher temperature, what happens is the vacuum expectation value gets a little bit less. Then there's some critical temperature where it's as likely, or it costs as much energy to have an expectation value as it does to not have an expectation value. And at even higher temperatures, eventually you get to the point where the Higgs would just like to have no expectation value. Yeah?
May I put a question?
Please.
So you say that the mass of the Higgs changes with the temperature?
The expectation value of the Higgs changes, and therefore the mass of the particles that get mass from the Higgs.
So that we have found the Higgs at 125 at a temperature which is 10 to minus 12.
That's right, which is very low temperature.
It's very low temperature.
Yeah, I would just say 0. Let's just call it 0. That's right. So what I'm saying, actually, that's right. If you could go to the early universe and look at the Higgs physics, you would find the mass of the Higgs would change actually as a function of temperature. In fact, the mass of everybody would change as a function of temperature. And there are two different ways you can imagine doing that, and that's the first and the second panel here. So in the upper panel, it's a first order transition where at some point, at the point where it's equally likely to have no expectation value or a non-zero expectation value, there's actually a potential barrier in between. And so that means that if I start off right at very high temperatures, I live in a potential that looks like the very top one where the Higgs expectation value is 0. Then at low temperatures, I know eventually I have to get down to the non-zero value we see today. If I'm living in a universe like in the top panel, then in order to go from the 0 expectation value to the non-zero expectation value, I have to tunnel through here. And that means that that process is usually a first order transition. It goes out of equilibrium. I'll say a little bit more about that in 1 second. The bottom process, though, if you look at the way that the potential depends on temperature, you can see that I start at 0 expectation value, but when I get to the equal point, I just kind of roll down to the minimum. So there's no barrier in between to stop me from getting there, and so the whole universe just evolves very smoothly from one phase to the next. It stays in equilibrium the whole time, and it's usually a second order or a crossover transition. So basically, whether or not we can use this to do something about baryogenesis, in other words, whether we can have an out of equilibrium condition, depends on whether the Higgs potential as a function of temperature looks like the top plot or the bottom plot. If it's the top plot, we're out of equilibrium, and there's some hope to satisfy the Sakharov condition. If we're in the bottom plot, then there's no out of equilibrium point, and therefore we can't. Yeah?
I have a question about this. Why you say that it is first order, it has to be out of equilibrium? I think it's more about the entropy, right?
That's correct, yes.
It's not actually a problem of equilibrium or not equilibrium, but of a change of entropy or not.
That's right. There should be a discontinuous change.
Okay.
Absolutely. So the way you can imagine this happening is that we start off in a universe where the Higgs expectation value is 0. So I call that the unbroken phase because it means the electroweak SU2 cross U1 symmetry is an exact symmetry. So the symmetry is not broken, it's unbroken. And then if I get to a point like this, where I have, like the top panel here, where I have a 0 expectation value in most of the universe, but it's possible at the same energy to have a non-zero expectation value through tunneling, what will happen is the quantum fluctuations in that field are going to say that every point in the universe, the value of the Higgs is jittering around in a quantum mechanical way. It changes a little bit. And eventually, one of them will jitter enough that it goes through the potential barrier and it lands here. Once one point lands here, it realizes it likes to be there because it has the same amount of energy to be here as it does over in the first place. So there's nothing to tell it to go back. Right? Whereas if I'd been up here, quantum mechanics can still sort of make me fluctuate up to a point over here, but then the energy is still much lower over here, so at that point we'll then go back to that original 0 expectation value. And so once I get here, then as the universe cools down a little bit more, this minimum, the one with non-zero VeV, gets lower. The minimum at 0 VeV doesn't get low as fast, and so it actually would prefer to be in that minimum. And so what happens is that little point that fluctuated forms a little bubble of what we call the true vacuum, right? That's the vacuum we live in. And that bubble is going to grow. It's a lot like what happens when you're boiling water, right? The water gets to 100 degrees, but it's still water, except that at that point, right at 100 degrees, you notice that I come from Canada and not the US because I said 100 degrees. Anyway, I just realized that that was true. So at 100 degrees, it costs as much energy to be water as a liquid as to be water as a gas. So what will happen is then, now there are no quantum fluctuations, but there are thermal fluctuations, right? The water isn't exactly uniform in its temperature. So a little bubble of the gas will form, and then that little tiny bubble that's microscopic will then start to get bigger and bigger because it actually, as the temperature goes a little bit above 100 degrees, it's actually better for water to be in the gas form than the liquid form. And so this is very much like that. It's like I've got the water, I've heated it up just to exactly 100 degrees, and then a bubble of the true phase, right? At 100 degrees, the true phase of water is the gas, forms, and the bubble gets bigger. Of course, eventually in water, it gets big enough that it floats to the top, and you know, there's no analog for that here. So here's my bubble. In here, I've got the true vacuum where the Higgs VeV is turned on. Out here, I have no VeV. The bubble is getting bigger, though, because it actually, as the temperature goes down through the critical temperature, it costs less energy to be in this phase than in that phase. So the bubble gets bigger until eventually it's our whole universe. So we live inside this bubble. Of course, actually, there may be some point way over here that's got its own bubble that formed. The bubbles will eventually get together. They'll collide with each other. That will release a lot of energy. And it may be that gravitational waves can teach us about that process. And so that's one of the things that's exciting that's going to come in the future from gravitational wave observations. The frequency is not the right frequency for LIGO. You probably need something like LISA, you know, the set of 3 satellites they want to put in orbit. That's the coolest physics experiment I've ever heard of, I have to say. Because the idea that you can control the position of 3 different satellites to like 1 centimeter, it just sounds crazy to me. But it seems like they can do it, so. Okay, so that gives us our out of equilibrium condition. And then the idea is that the CP violation makes a bias so that it's more likely for quarks to go into the broken phase than antiquarks. And so we end up with a non-zero amount of baryons inside here. And this is called electroweak baryogenesis. It's just the baryogenesis that's in the standard model by itself with no additions. So as a result, there's a strong connection between the Higgs physics and the electroweak phase transition. And that's because we can calculate the thermal potential for the Higgs boson. So it has these terms at 0 temperature that we're used to seeing that give us the Higgs expectation value. So there's a mass term and a quartic interaction. Remember, the Higgs mass is related to the expectation value times the quartic. So when we measured the Higgs mass, we found out what that parameter was. That's the last thing in the standard model we didn't know, but now since 2012 or so, we know what it is. And then there are the temperature-dependent corrections. And these are a little complicated. I don't want to go through them in great detail, but basically they just are summing up all the stuff that's in the universe at that time. So you sum over all the different kinds of particles. You integrate over all their momenta, and then times the distribution of what momentum you expect them to have at that temperature. Remember, beta is like 1 over the temperature. You have to remember your stat mech a little bit. And it depends on how their masses depend on the Higgs expectation value. The plus or minus are for fermions and bosons, just like normal. So if you do this calculation, you find the potential, and you ask, what does it take to get a first-order phase transition? Well, back when people started doing this calculation, they already knew what the Higgs expectation value was because they knew what the W and Z masses were. They also knew about the masses of all the other particles in the standard model. So the only parameter that they could play with was the quartic lambda. So they put their answer as a function of lambda, and they found out that in order to have a first-order phase transition, lambda has to be smaller than some value, and then I turn that back into the Higgs mass, and it says the Higgs mass has to be less than 50 GeV. So the only real reason this whole process didn't work is because the LHC discovered the Higgs and the mass is too heavy. Actually, already by the time of LEP, we already knew that this mass was ruled out, and so we already knew it didn't work back then. And it's very close to working, right? 50 GeV, you know, if your answer had been it has to be less than 1 EV, you would have said, okay, there's no way I'm ever going to rescue this, because there's nothing I can do to make such a big change to this potential by adding physics beyond the standard model. But instead, it's only off by a factor of 2 or 3. So you could imagine maybe there are some more particles I could put into this game whose masses depend on the Higgs, and if I add those new particles, I could actually change the calculation such that 125 GeV would work. And actually, this is why people still talk about baryogenesis for theories like the minimal supersymmetric standard model. Right? It adds a bunch of particles, they couple to the Higgs because they're superpartners of the standard model particles, which couple to the Higgs. And so you can actually make this work by just adding the right kind of new particles. And that's actually what the MSSM does. Or you can add new kinds of Higgses to the Higgs potential. That's another thing that people do a lot of. Okay, and then finally, just to finish up about baryogenesis, the standard model also doesn't have enough CP violation to explain the magnitude of the baryon asymmetry. The CP violating phase enters all physical observables as a Yarlskog invariant. That's just an invariant because you can do change of definitions of what you call an up quark versus a charm quark versus a top quark. The Yarlskog invariant tells you what the invariant measure of CP violation is in a theory like that. It turns out that it's proportional to the Yukawa coupling squared. It's the product of them. And if you look at that, it gives you an answer for CP violation that's about 10 to the minus 20 or so. It's just too small. There's not enough CP violation in the standard model. It's actually not small because the phase is small. The CP violation in the quarks is actually a big phase. But it's because this is normalized by the masses of the quarks, and it's because the up and down quark masses are very tiny. And that suppresses the effective CP violation. So it's not enough to actually explain the baryon asymmetry that we observe. So that means that in addition to fixing up what happens with the Higgs, you would also have to add new sources of CP violation to the standard model to make baryogenesis work. And you might have heard about something called leptogenesis. Leptogenesis basically gets the out of equilibrium condition by asking for there to be heavy neutrinos that decay, and then gets a CP violation from the neutrino masses. And there we don't know enough about the CP violation to be sure that it doesn't work. In fact, it looks like more likely than not it would work. So that's another idea, but it doesn't connect with the electroweak transition. Okay, so that was sort of my little survey of Big Bang nucleosynthesis, baryogenesis, and the electroweak transition. As you can see, in my mind, these things are all connected, but they're each one individual things that you can talk about. And then I want to spend the rest of the time talking about dark matter. I realize I don't have any way of knowing how long I'm talking, so I may talk for too long, but you can always yell at me.
You're doing fine.
That still doesn't tell me how much time I have left.
15 minutes.
Okay. I'll try to go a little faster then. So dark matter is another important ingredient in our universe. We have evidence for dark matter from many different scales of observation. So the CMB itself actually tells us that there's some kind of fluid that wasn't coupled to photons, but was massive. It was non-relativistic at the time the CMB formed. We have things like how structures form. So we look at the patterns of galaxies we see around us, and we can tell that if we just had baryons in the universe, we wouldn't have as much of a rich structure of galaxies as we see. We wouldn't get a universe like the one we see. So we do simulations that show if you add dark matter, you get the right amount. And you've probably all seen this plot of the bullet cluster from gravitational lensing, which also tells us that there are things that are lensing light that comes towards us that are not accounted for by the baryons. This is, again, it's a pretty old plot. It's from 2010. It's the density of the matter in terms of the critical density, and then compared to the density in dark energy. And the reason I like the plot is that you see that there are different kinds of measurements. So, for example, the supernova measurements, looking at how the brightness of supernova varies with how old they are, how far away they are. The CMB measurements, the baryon acoustic oscillations are things related to structure formation. They all agree that we live in a universe that has a large amount of dark energy and a large amount of dark matter. So, the reason I got excited about this is because any two of these things, well, first of all, two of them didn't have to overlap, right? You could have had your ellipse over here and the baryon acoustic oscillations could have been over there. That would have been possible. But the fact that all three of them really line up in the same place is a really strong clue that this model where we add dark energy and dark matter is probably correct. So then the question for particle physics is, what is dark matter? This is actually a sculpture which is called Cold Dark Matter, an Exploded View. If you've seen me give a talk before, you've seen it, I'm sorry. It's a three-dimensional sculpture. You can walk around, you can look at it. It's in the Tait Modern Museum, but Tait is not spelled correctly, so don't get confused. That's in London. And the way I see it is, if you look at this beautiful thing that the art world can create based on us telling them that dark matter exists, I'd really like to see what kind of sculpture you could make if we could tell you what dark matter actually is. So what we know about dark matter is pretty modest. We know that it's dark, that's in the name, which means it's neutral. It doesn't have electric charge, it doesn't shine. It's massive, which means it's non-relativistic, it doesn't move very fast, and it's still around today. So most of the particles we know in the standard model that have these properties decay very fast, and they can't be dark matter because it wouldn't be there making up the galaxies at this point. So that means that it's stable or it has a lifetime that's about the size of the age of the universe itself. It might be dark matter is really slowly decaying and we just haven't noticed yet. And nothing in the standard model of particle physics fits this description. So here's our table of the fundamental particles that we know. There's actually an updated one with the Higgs, but I had to add the Higgs myself back when I made this slide. Basically, all of the things here either have electric charge, that rules out all the quarks and the charged leptons. It also rules out the W boson. It also really rules out the gluons because they're stuck inside stuff that have electric charge too. Neutrinos could actually have been the dark matter, but they're too light. Neutrinos wouldn't cluster together and form galaxies like the galaxies we see. They're just so light that they fly away. So neutrinos don't work because they're too light. And then the last two things, the Z boson and the Higgs boson, they are massive and they are electrically neutral, but they decay very fast. Right? The Higgs boson decays in less than a femtosecond, and the same thing for the Z. So there's no way that that explains dark matter in a universe that is like 10 billion years old. So that tells us that dark matter has to be a manifestation of physics beyond the standard model. We have lots of ideas for what dark matter could be. So this is a Venn diagram of different theories of dark matter showing how they're related to each other. So what they all have in common is they're all a theory of dark matter. These are all real theories actually that people work on. I don't know if the value of this diagram is more in the direction of abstract art or if it's actually informative, but anyway, it was fun to make. So the idea is there's no lack of theories for what dark matter could be. It could be any of the things here, and in fact, this diagram was made in 2013. There were at least 2 or 3 more things that I feel like should be added at this point that weren't there at the time. And the parameters for dark matter are very wide-ranging. So the dark matter mass could be anything down to about 10 to the minus 33 or so GeV, all the way up to about 10 to the 18 GeV or so. And that's really just because this is the Planck scale, and beyond that there's quantum gravity, and it wouldn't really make sense to talk about particle physics the way we normally do. The interaction cross-sections, again, it could be very strongly interacting. More likely it's weakly interacting. And so there's a whole bunch of these theories we saw on the previous slide that live at different points here. I'm going to focus today really on things that are either WIMPs or close to WIMPs. That live sort of around here. So their masses are around, say, a GeV to a TeV or so, and their interaction cross-sections are not super weak, but they're obviously not super strong either. Similar to what neutrinos have as their cross-section. This is a plot that Sasha Belyaev makes, which is the number of papers on different topics as a function of time. So you can see that Susie is sort of plateaued. Higgs keeps going up, right, because the Higgs is still new and exciting. Extra dimensions is not doing so well because we haven't discovered any extra dimensions. The top is doing, again, pretty well because, again, the top quark is always there and always exciting. I started out studying the top quark in my thesis when I was in graduate school. And dark matter is something that's really taken off as time has gone on because, again, it's something that we know exists. So this is what I call the dark matter questionnaire. These are all the things we want to know about dark matter and the one thing that we do know about it. So we want to know the mass, the spin. Is it exactly stable or is it just approximately stable? What does it interact with? So we know it interacts with gravity because that's how we know it's there. But basically everything else, all the particle physics questions are all sort of totally open. In fact, since we know that gravity is really just the structure of space-time, it would be really weird if it didn't interact with gravity. That's hard to imagined. So basically our job in particle physics is to try to fill in all the rest of these entries. So one of the things about dark matter that's a big clue as to how you would build a theory containing dark matter is that it has to be at least quasi-stable. It has to do a very good approximation to be stable. And what that means is that we can't allow for interactions that have one dark matter particle that are talking to the standard model particles. At least we have to suppress those interactions by a large amount. And it's because this kind of diagram would let the dark matter come in and then just decay into a bunch of standard model stuff. So what we need is a symmetry that would prefer for there to be two dark matter particles involved in each interaction, or at least an even number of dark matter particles to be involved. And in that way, the number of dark matter would be conserved. And this doesn't have to be an exact statement. It might be that there are some kinds of interactions like the ones on the top that are allowed, but they have to be so suppressed that the dark matter's lifetime turns out to be the age of the universe. So that's really, really, really suppressed. These interactions have to be like the size of the gut scale or something like that. Very close to the Planck scale. And if you know about building theories in particle physics, then that would tell you that a symmetry would be a good idea to try to make this kind of interaction with two dark matter particles the dominant one. And the easiest symmetry is Z2 symmetry. That's like a parity, right? So if the parity just says that the dark matter field goes into minus the dark matter field. And so if I want to build a theory that conserves dark matter number, that parity tells me that to have an invariant, I need to have two dark matter particles so that I get two minus signs and I go back into myself. You could actually explore different symmetries as well, and that's interesting. It's just not what I'm going to do here because it's not minimal. And then another very attractive proposal for dark matter is a weakly interacting massive particle, or a WIMP. WIMPs naturally account for the amount of dark matter that we see in the universe. And they also occur in most of our favorite theories for physics beyond the standard model, like in supersymmetry or some kinds of extra dimensions. And they're also a vision for dark matter which we can use particle physics experimental techniques to search for very effectively. So in some ways that might mean that we're looking under the lamppost, right? We're looking where it's easy to look, but of course you're going to start off looking where it's easy, and then if you don't find anything there, you're going to look where it's hard. So people kind of bring this up like a criticism, but I think it's just physicists being rational, personally. This is another image I found on the internet. It turns out you can buy dark matter. It costs about, I usually translate into euros, I forgot to do that here. It costs $60 for 20 servings. It's a bottle about this big, apparently. I guess if you read the fine print, it builds muscle mass, so that's why WIMPs need it. Maybe. I think the most important thing is that this stuff comes in blue raspberry fruit punch and grape flavor. I don't know what that means, but it sounds pretty important. Actually, the reason I like it is because there are 3 flavors, just like maybe there are 3 flavors of quarks and 3 flavors of neutrinos and 3 flavors of electrons. I want you all to solemnly swear that if we do discover that there are 3 flavors of dark matter, that we make sure that these are how we call the flavors. Oh, I have a friend in Korea who actually bought this stuff so he could take it out in talks and show it to people. And he told me one very important thing. It tastes absolutely disgusting. Which I think he probably could have guessed based on the flavors, but he said his kids like it. So, all right. So what I want to go through is, I want to go through this argument as to why WIMPs naturally account for the amount of dark matter in the universe. That's really the best reason to think WIMPs might be the dark matter. And of course, this argument I'm about to make, there's nothing that guarantees it has to be what happens in nature. It's just our best guess for what happens, and so it's where we start. So the primary motivation for WIMPs is this idea that we can understand the abundance of dark matter. This is usually called the WIMP miracle, which I don't really like as a name, but I have to live with it. And so I'm going to go through the argument that basically tells you how much dark matter there should be, because I think that's one of the most important things to take away. So the picture starts out with the WIMP at some early time when the universe is small and it's hot, and the dark matter is in chemical equilibrium with the standard model plasma. So this little cartoon here shows you a little box of a part of the universe. It's filled with the standard model plasma, so there's a whole bunch of high energy standard model particles living inside this box. And there's a bunch of dark matter particles living inside here too. These guys are interacting with each other, so since I like the idea that the dark matter is stable, I want 2 dark matter particles to interact with some number of standard model ones. And so that's a process where now dark matter can turn into the standard model, or if I'm in equilibrium, that means it's equally likely that the standard model turns into dark matter. In other words, the energy of this plasma is high enough that it can produce the heavier dark matter particles by making the process run backwards this way. And how likely that is to happen depends on the size of the cross-section for this process. This is the annihilation cross-section for dark matter into the standard model. So, okay, so in equilibrium, there's really nothing to talk about. We have some amount of dark matter, we have some amount of standard model stuff, there's a temperature that describes the whole system, and the relative amount of dark matter versus standard model is just controlled by the temperature and the masses of the particles. So, and that's shown here by this equilibrium number density, which is just the Boltzmann distribution you learned in stat mech. So, if I want to describe how the density of dark matter changes in time, there's a Boltzmann equation I can write down, and it looks like a very standard Boltzmann equation where I have the number density of dark matter differential in time. And then over on this side, what I have is the cross-section, which tells me how likely the dark matter is to turn into standard model or vice versa. And it multiplies something that looks like the number of the dark matter squared minus the equilibrium density. That's the Boltzmann distribution. So what this tells you is that the dark matter would like to be at the equilibrium density. If I have too much dark matter, right, then n squared is bigger than n equilibrium. This is a positive number. There's an overall minus sign here, so the dark matter goes down to equilibrium. And conversely, if I have too little dark matter, this whole thing is negative, and the dark matter goes up to get to equilibrium. So that just tells you the equilibrium is where the system wants to be. Now the part here that's interesting that I didn't mention yet is this plus 3hn. H is the Hubble constant that tells me the universe is expanding. So the thing that's different about this in an ordinary stat mech system that you solve in graduate school is that my box is actually expanding because the universe is expanding. And so what happens is eventually this term is going to become important and it's going to dominate over the second term. This is usually called the collision term. So when the expansion of the universe dominates over the collision, I get to a point where I'm no longer in equilibrium. And that's why things are interesting. Because in a universe where the WIMP stayed in equilibrium, it would be very boring. And that's because the Boltzmann distribution here at the bottom, as the temperature gets lower and lower, right, which is what happens when the universe expands, it becomes exponentially small. So if I were to stay at equilibrium, there would be no dark matter left in the universe at the end of the day. Right? The universe would just keep expanding, the temperature would get lower and lower. What that means is when the temperature is below the mass of the dark matter, it's more likely for the dark matter to go into the standard model than the standard model to go into the dark matter because there's not enough energy to make dark matter particles at that temperature. So I have to get out of equilibrium in order to avoid having no dark matter left. Okay. And so that's where that second term comes in useful, this expansion term. So at some point the expansion becomes more important than the annihilation of the dark matter. And at that point, the dark matter stops actually tracking the equilibrium density. And what you can think of physically is what's happened is the universe starts out here at the top with lots of dark matter, lots of standard model, and a high enough temperature to go back and forth between them. But as it expands and cools, I get to a point like the bottom where I still have all the standard model stuff. It's at lower temperature now, but it's still there. But now the dark matter has been diluted to the point where there's not very many dark matter particles. Right? I've fallen down that equilibrium curve to the point where the dark matter is pretty much isolated. Now I can't find another particle to annihilate with. And once that happens, I stop tracking the equilibrium density. Right? I can no longer get rid of dark matter particles because they are so diffuse in the universe that they can't find each other to annihilate. And I assume my interactions were such that they need to annihilate in a pair. So this process, the time when the Hubble expansion becomes similar to the collision term, that time is called the freeze-out time, or the temperature where it occurs is called the freeze-out temperature. And so that's where the word freeze-out comes from. And at that point, they stop tracking the Boltzmann distribution. Where exactly freeze-out happens depends on the size of the cross-section, because that's what tells me at what point the expansion is equal to the collision. So, of course, I presented this in sort of a very heuristic way, but I can just solve this differential equation numerically, and that's usually what people do. You put it in Mathematica and you find a solution. So if I do that, I'll get a curve that looks like this one. So what's plotted here is the temperature of the universe is on the x-axis, and if you look at it, it starts at sort of about 30 GeV or so, goes down to maybe about 300 MeV, or no, yeah, something like that. So the temperature is getting lower as I go along the positive x-axis, and that means that it's like time increasing. So you can, this is written as temperature, but you can think of it as time is going up this way too. And then on the y-axis, I have the density of the dark matter, which is just normalized to some kind of arbitrary value at the beginning. So at the beginning, I have some amount of dark matter. It's in equilibrium. I see the equilibrium exponential fall off, and then I see that my equation actually does predict that the dark matter stabilizes. And that's when I fall out of equilibrium right around here, and then the dark matter stops annihilating. So this equation does actually have the solution that I was talking about. If I track the different parts of it, right, we start off with the dark matter in equilibrium with the standard model plasma. As the temperature falls, the number of WIMPs does too, right? It tracks that Boltzmann distribution. At freeze-out, so freeze-out is when the number of dark matter, which I'm assuming is close to equilibrium. So I wrote the equilibrium number, but even if I put the number of dark matter, it's the same thing at this point. Times the cross-section is similar to the Hubble expansion. You can sort of plug in some guesses for what that would look like to find out when that happens. So that's right about here, where the red dot is. And then going further, I get to the point where the annihilation doesn't matter anymore. The amount of dark matter becomes fixed, and then that's how much dark matter we get. So the important point to take away here is that where exactly that freeze-out happened is a function of the cross-section. And therefore, if I had a higher cross-section, I would stay in equilibrium longer, I would freeze out later, and I would have less dark matter. If I had a smaller cross-section, I would freeze out earlier, and I would have more dark matter. Yeah?
If I understood correctly, you have to assume a form of the Hubble constant with temperature?
Yeah, so I assumed it was radiation dominated, that's right.
That pretends that you have a model for that. Together with the non-equilibrium Boltzmann equation, you have to add some kind of cosmological model.
Absolutely. So the assumption here is, the standard assumption that's being made is that I have the standard model plus the dark matter. The dark matter is non-relativistic at the time of freeze-out, so therefore the standard model dominates. And now this depends on what the dark matter mass is, but if the mass of the dark matter is around 100 GeV or a TeV or something like that, then it will freeze out at a temperature of something like maybe 10 GeV or 5 GeV. And at that time, the universe is radiation dominated if I just take the standard model into account. Right? That's a time when we still have quarks and gluons, and there's lots of degrees of freedom that are very light. And so the universe will be expanding under the radiation that's dominating it. Of course, the calculation changes a little bit if I change those assumptions. The overall picture doesn't change that much. So even if it freezes out during a time of matter domination, the parametrics are a little bit different, but the actual story doesn't really change. Okay, so it's sort of amazing that actually this argument for the amount of dark matter, first of all, it's very nice because it doesn't depend on any of the real details of the early universe. You just assume the universe was there, it had some temperature that was pretty high, and there was some dark matter in it. And then everything else is controlled by equilibrium densities, so there's no dependence on any initial conditions or anything like that. And the amount of dark matter you get is connected directly to the particle physics quantity. How much does the dark matter interact with the standard model? So, so this would actually then suggest that there's a cross-section that is the most favored cross-section if you want to explain the amount of dark matter that we have today. All right, so then ideally what we would like to do is measure dark matter interactions with the standard model. And if we could do that, we could actually check out the relic density. Right? If we understood all these interactions, we could calculate the annihilation cross-section and then see if it matches the predictions we need to get the amount of dark matter that we have. And I think that many people will phrase this in a different way, but I think that we should see this from a very experimental point of view. What we really want to do is we want to check to see if this picture for the universe is correct or not, because we don't know if it's correct. So therefore, the most important thing is to measure these interactions and then see if you can predict the amount of dark matter. And if you can, you would say, okay, I understand what's going on. If you don't, then you would say, okay, I'm missing something. And it might just be that I'm missing something like I made a bad assumption for the cosmology. So that would also be a hint as to that. So the moral of the story is some people would like to impose this as a requirement on the theory of dark matter, but we shouldn't do that because we don't really know that this story is correct. Right? What we have to do is check to see what the story tells us. So then the last little part of this, I'd like to talk about some of the detection strategies. So the three main ways that particle physics searches for dark matter is dark matter can annihilate. That's what we've already talked about quite a bit, which is called indirect detection. So the dark matter produces standard model particles. We then try to detect them. This is a picture of it's actually an artist's conception of the Fermi Large Area Telescope, which looks for gamma rays. We could try to look for the dark matter scattering with standard model particles in a detector in the lab. That's called direct detection. I believe this is a picture of the xenon experiment in Gran Sasso, which is doing that with a two-phase xenon detector. Or we could try to produce the dark matter in the laboratory at high energy reactions where we have enough energy to produce the dark matter particles. And of course, that's what we're trying to do with the Large Hadron Collider in part, along with many other things. So the dark matter model predicts the rates of these processes and also how they're related to each other. If you know what the theory of dark matter is, you can calculate each one of these things. If you don't know what the dark matter model is, which we don't, then you have to look for all of them and try to figure out which one is the most likely to give you a detection. And depending on the theory, you can easily find parts of the parameter space where one of them is going to be better than the others, but you can also find different regions of parameter space where another one's going to dominate. So you really have to do all of them if you want to find out. So I'm going to go through them very quickly. I must only have a few minutes left, I guess.
But please go ahead.
Okay.
Go ahead, go ahead.
Right. So indirect detection tries to see dark matter annihilating. So in general, right, we just argued that the dark matter is so diffuse that in general it can't find itself and annihilate. But since the time of freeze-out and now, what happened is the dark matter all collapsed into galaxies. So there are parts of the universe where the dark matter density is very high. Right? We happen to live in one of them because that's where all the stars are. So therefore, there are parts of the universe where this process is still happening, like the centers of galaxies. And so if they sometimes find each other and annihilate, then we can try to detect the particles that are produced in the annihilation on the Earth. You hear a lot of discussion of photons and neutrinos, and that's because photons and neutrinos both interact weakly with the stuff that's in the universe now, weakly enough that they have a chance of getting to us, and we can detect them and see where they come from. So that doesn't mean that it is interesting to look at charged particles like maybe antiprotons or positrons or even antinuclei. The only difference, though, is that because of the magnetic fields in the galaxy, those particles change direction on their way to get to us, so we don't know where they come from. However, you could still find an excess of them, and it would still be interesting. And in fact, if you've heard about the AMS experiment that's on the space station, it has found that there are interesting excesses of these particles. So we don't know if they come from dark matter annihilation or not, but they are certainly an interesting feature of the galaxy. Since the dark matter is neutral, let's just talk about photons. It doesn't couple directly to photons, but what we can do is, since the dark matter does couple to charged particles, it's like maybe W's, quarks, whatever, those particles will eventually produce things like pions, and we know pi zeros decay into 2 photons. Pi pluses will produce things like neutrinos and positrons. And so actually, even though we don't couple directly to photons, we get lots of gamma rays, and largely they come from production of pi zeros. But what that means, though, is that the energy of the gamma rays is not directly related to the mass of the dark matter particles, because in between here, you have to produce some other heavy guys. Those things decay, so the energy gets shared. Then eventually they hadronize, so you get the pi zeros. So the energy you get in the gamma ray is a small fraction of the energy you get inside the parent particle. And if you look at this as a function of the final state, so this is a 1 TeV dark matter particle, which is annihilating into a pair of either W, Z, top, bottom Higgs. This is this mess of curves right here. The colors tell you which one is which, so you can see. And it's a log plot. So this is the energy of the photon as a function of, the x-axis is the energy of the photon. The y-axis is the log of the number of photons at that energy you get. Since it's a log plot, well, so first of all, actually, it's a 1 TeV particle. So you never get anything higher than 1 TeV, right? That's as much energy as I could possibly get in this reaction. And then again, because it's a log plot, all of the photons that come from these particles, W, Z, T, V, H, are all very, very low energy. Right? It seems like this goes pretty high, but your eye is sort of being fooled by the fact it's a log plot. Instead, if it goes to taus, electrons, or muons, you actually get a much harder spectrum where you're much more likely to get high energy particles. From the electrons and muons, that's from Bremsstrahlung. From the taus, it's because taus decay into pi zeros, and pi zeros give you photons. But the thing is, if your dark matter goes into 2 taus, each tau will have an energy of 1 TeV, and then each tau can only decay into a couple of pions, and so each pion gets most of the energy that it started with. And that's why you get a much harder spectrum from the taus than from anything else. Which is sort of interesting. It's very difficult to detect dark matter interacting with taus at the LHC, because the LHC doesn't collide taus, or in direct detection, right, because our detectors are not made out of taus, they're made out of electrons and nuclei. So, but taus are by far the best particle for them to annihilate into if you want to see indirect detection. All right, so there are packages you can use. They're all based on Pythia. You know, Pythia is the thing that showers and hadronizes and decays particles to give you a prediction for what you should get here. That's how this plot is made. And you can then look for this type of annihilation. So here's 2 dark matter particles annihilating. In this case, they assumed it annihilated into bottom quarks. They like bottom quarks because in supersymmetry, for a lot of the parameter space, bottom quarks dominate. Here's the cross-section you would need to get the relic density. So that's that cross-section we saw before. And then here are the bounds that the Fermi Large Area Telescope gets looking for photons that come from dwarf galaxies. These are little galaxies that are orbiting our galaxy. And they're good targets because they don't have a lot of stars and other stuff in them, so they don't have a lot of background. That's why they like to use them. And you can see that basically the Fermi measurements, if the dark matter has this thermal story for its abundance, they rule out masses less than about 100 GeV or so. Again, if it annihilates into bottom quarks. For higher masses, they still rule something out, but it's higher. And of course, you know, these could still be good dark matter models, they just don't have that thermal relic story. If you were to discover it up here, then you would say, okay, I have to go back and figure out how to fix up my cosmology to make that the amount of dark matter that works. You can also look for a process where the dark matter annihilates directly into 2 photons. And that gives you a line, meaning a monoenergetic source of photons, whose energy is related to the dark matter mass down here, and also the mass of the second particle it annihilates into. And you can also get bounds by looking for those features. And that's a nice thing to look for because it's very different from astrophysics. Astrophysics sort of never gives you all the photons at the same energy. And you can, however, there's no direct connection to the freeze-out story. The reason I like this plot is because what they've done is this is exactly the same bound. It's exactly the same data looking for a gamma ray line as a function of the dark matter mass. But what's interesting is they've changed a model for what our galaxy looks like as it's made of dark matter. So this one is a kind of Navarro-Frank-White model. Here's another Navarro-Frank-White model. Here's an ASTO profile, so it's a different model for how our galaxy is made out of dark matter, and then isothermal. This one's not really very realistic, but these other 3 are actually all consistent with what we know about our galaxy. Which means we don't really know if the limit is this one or this one or this one. So there's also big uncertainties in this process because we don't really know the astrophysics we need to predict it very well. Then direct detection, the basic strategy here is to look for dark matter coming in and interacting with either a nucleus or an electron and seeing the recoil. Right? So the dark matter comes in, there's some shielding to make sure that no charged particle came in. It interacts with the nucleus. Dark matter goes out, again, doesn't interact, but we see the nucleus bouncing around as a result. There's an interesting handle on this, and that's because the rate of dark matter that's hitting the Earth is different at different times of the year. The reason is that the dark matter itself is not actually moving compared to the galaxy very much. It's moving, but it's just moving in random directions, right? Because the dark matter is the galaxy. Most of the mass of the galaxy is dark matter. But the sun is moving with a definite speed around the center of the galaxy. So therefore, as the sun moves, it effectively sees a wind of dark matter coming towards it because the dark matter didn't have any net motion. So there's some amount of dark matter that we think is likely to be coming towards us because the sun's moving. But at the same time, the Earth is moving around the sun. So when the Earth is going in the same direction as the sun, then the dark matter incident on the Earth is bigger because these 2 velocities add up. And when the Earth is moving away in the other direction, in December, then it's actually moving in the opposite direction from the sun, and the wind of dark matter seems to be a little less. So the amount of dark matter that's hitting your detector should actually vary as the course of the year does. Now, unfortunately, lots of other things also vary over the course of a year. The temperature, the rain. But this is an interesting handle that you can try to use to learn something about this signal. And then also, in the particle theory, we need to know how the dark matter interacts with quarks. In the particle theory, it predicts how dark matter interacts with quarks and gluons. However, in direct detection, there's a very small amount of momentum transferred. So the dark matter actually doesn't see individual quarks and gluons, but actually it sees the entire nucleus. And there are two different ways the dark matter can interact with a nucleus. It can either interact independently of the spin, so it just sees a nucleus like a ball of stuff that it likes to talk to. And if that's the case, there's a big enhancement here because the momentum transfer, you probably learned a million years ago in quantum mechanics class that the momentum transfer corresponds to the effective wavelength that you sample your target on. So the wavelengths here are typically bigger than the size of the nucleus. So you see the entire nucleus and all the nucleons inside it, all the protons and neutrons. So you get to add them all up and you get an enhanced reaction for scattering. So spin-independent bounds are usually the strongest ones for that reason. Or the dark matter interaction might be such that it interacts with the spin of the proton or neutron. That's called spin-dependent interactions. And there it's not enhanced because what will happen is the spin of the nucleus is going to be comprised of the individual spins of the nucleons all added up in some way. But we know that from the nuclear shell model, the spins like to pair themselves, spin up and spin down. So usually you get very small spins for nuclei. Very few nuclei have big spins. And so that doesn't give you a big enhancement like the spin-dependent does. And in the non-relativistic limit, these are the only two things, the only two ways that dark matter can interact with the nucleus. Everything else is suppressed by the dark matter velocity. Which is, of course, still interesting to look for, but these are the most promising ones as a result. So here's again a plot. This one's from the Xenon 1-ton experiment. This is dark matter coming in and interacting, let's say, with quarks. So this is as a function of the dark matter mass. And you see their limit. The limit has sort of two features that are interesting. At high masses, the limit kind of asymptotes to a line like this. And what sets this line is just the fact that as you make the dark matter more and more heavy, then because the energy density is the thing that's constrained by the gravity, as you make the dark matter heavier and heavier, the number density has to go down by the same amount. And so you're just seeing the fact that there's less dark matter around as the mass gets bigger. And then at low energies, there's a threshold for the detector. The dark matter that's too light can't give enough momentum to the target, and therefore it can't really be detected. So there are lots of specialized detectors that are built to try to explore lower masses. And so they don't even actually have, well, Panda X is another xenon experiment like Xenon 1-ton is shown here. And you can see that specialized detectors like CDMS Light or DOMIC are actually able to go down below to lower masses around a GeV or even less. And that's very exciting because we never looked there.
5 minutes?
5 minutes? Yeah. Actually less probably. Sorry. And the last one I wanted to mention was collider production. If the dark matter interacts with quarks or gluons, we should be able to produce it at high energy reactions like at the LHC. So we can look, for example, like production of the dark matter along with a jet of hadrons, so that there's something we can see in the detector. This is called a monojet search, where we have missing momentum, something that doesn't interact with the detector, balanced against a jet of particles. This is usually plotted as in the plane of, say, the mass of the mediator particle that produces the dark matter and the mass of the dark matter itself. And you can exclude regions of parameter space that look like this. So there's an upper limit to what you can exclude, and that's because at some point there's not enough energy to produce those events. And then it has this kind of wedge shape because if there's some mediator particle living inside here, then basically you want the mass of that mediator particle to be heavier than twice the mass of the dark matter so the mediator can decay into it. And that's why you get something like this. This shows you actually what cross-section is excluded for every point in this plane. The place where you get the right relic density is shown by this line. So you're actually saying something interesting about the thermal relics. There's another region up here you're not saying anything about that. You can also translate that into the same parameter space as we saw before. So this is the mass of the dark matter versus, in this case, the spin-dependent cross-section with the WIMPs. And this compares something that Atlas excluded, is the black line, compared to the Pico 60, which had strong limits on spin-dependent interactions with protons. And then finally, you can also look directly for mediating particles themselves. So two quarks can get together, produce a mediator, and then instead of going to dark matter, they could actually decay back into quarks. And so this looks like a resonance in jets. And there's a lot of interesting work that's been going on putting limits on the mass of these mediating particles, so it's called Z prime here, as a function of its coupling to quarks. And in fact, we've been really creative stuff done at low masses because there the triggers become a problem. So to finish up, at early times, the universe is very hot. The stuff living in it has high energies, and it needs to be described by the language of particle physics. The observations reveal mysteries of the universe that particle physics can help out with. So for example, there's a period of inflation, an asymmetry between matter and antimatter, and then the existence of dark matter, which is not part of the standard model, and of course dark energy, which I didn't talk about. And these are all observational motivations to extend the standard model and tell us how we can add new physics to it. The ingredients they suggest are the kinds of things particle experiments can look for. So they can look for new physics coupled to the standard model Higgs boson, new sources of CP violation, and something to be dark matter, electrically neutral particles which couple to the standard model with large couplings. It's not clear that our current experiments necessarily will be able to access this new physics, but it's exciting that we keep pushing into new territory where we could make a discovery. So there's no guarantees, but on the other hand, there's a lot of reason to be excited. And we have many theoretical ideas that we hope the experimental results can bring to life. So this sketch by Escher is supposed to show how experiments bring theories to life. I also like the fact that they seem to be bringing each other to life, which I think is also true. And this is my favorite sketch of dark matter. So thank you, and sorry for going over.
We have time for some questions.
Yeah.
You're reading the cartoon.
Yeah, we're reading the cartoon.
Sure.
Yeah, I have a question. It's regarding the phase transition. If can you distinguish between the first order and second order and looking at cosmological perturbations? Because I think that in the first order transition you are generating entropy fluctuations and the isocurvature modes, which are constrained with the CMB, for instance. I don't know if you can put constraints.
Yeah, so the usual thought for the electric transition is it happens so early that probably the fact that you go back to equilibrium in the middle will probably erase the isocurvature modes.
Yeah.
However, certainly things like gravitational waves could survive. That's the thing that people talk about the most. In principle, you can imagine there's some other kind of phase transition that maybe happens a little later, and then you could definitely try to detect isocurvature modes, and there are constraints actually on that kind of thing happening. People talk about that a lot when they talk about the axion. The axion has a phase transition that's different, but it could happen at a different time, and then it might be observable. That's right.
The Z prime, the mediator masses that you were talking about in your next to last slide, that does not seem to, I mean, how can that be compatible with a long-lived dark matter? It seems
Well, so yeah, in this theory, right, the dark matter is not the Z prime. It's something that talks to the Z prime.
Okay.
So yeah, the Z prime itself here is not dark matter, and that, in fact, you can see, right, if you just had a Z prime to begin with, it decays into two quarks, and it's gone.
Okay.
So yeah, but for all of these parameters that are being discussed here, it lasts, a very small fraction of a second. It's not stable itself.
Some other questions from the general public? No? So thank you very much again.